All right, let's talk about the single most important shortcut in all of calculus. Seriously, we're about to uncover the one theorem that connects everything you've been learning. All those hours finding slopes, all that tough work calculating areas, this is where it all finally clicks together.
So I want you to think back for a second. If you've been in a calculus class, you know the feeling. Trying to find the exact area under a curve. You're drawing all these little rectangles, you're making them infinitely skinny, you're wrestling with limits. It's a ton of work, right? And it definitely leaves you wondering, oh, there has to be a better way to do this.
And look, that whole process, what we're calling the calculus grind, it's super important. It really builds the foundation so you understand why integrals work the way they do. But, actually doing it that way all the time? Yeah, no thank you. There is a much, much better way.
You've already put in the time, you get it now, that finding an area is really about adding up an infinite number of tiny, tiny pieces. You've battled with derivatives to find slopes, and you've conquered Riemann sums to find areas. You've done it the hard way. And honestly, that's a good thing, because it means you're ready for the secret.
So let's go ahead and build that bridge. It's time to reveal the great shortcut, the really elegant connection between these two huge ideas in calculus that, up until now, have probably felt totally separate.
I mean, think about it. Differentiation and integration probably feel like they live in completely different universes. On one side, you've got derivatives, which are all about slopes and instantaneous rates of change. And then way over on the other side, you've got integrals, which are all about adding up area under a curve.
But what if they aren't so different after all? Let's just think about basic math. You know how addition and subtraction are inverse operations? One just undoes the other? Same thing with multiplication and division. They're like two sides of the exact same coin.
And that's it. That is the huge light bulb moment. What if these two giant pillars of calculus, differentiation and integration, were just inverse operations? What if one was perfectly designed to undo the other? Well, that simple idea right there is the secret of the fundamental theorem of calculus.
So let's pop the hood and see how this thing actually works. The theorem officially comes in two parts, and together they give us the mechanics for how this amazing shortcut functions.
Part 1 really just shows you how beautifully symmetric this whole thing is. What it's saying is that if you do these two operations, one right after the other, first you integrate a function and then you immediately differentiate that result, boom, you land right back where you started. They literally cancel each other out.
So here's another way to think about it. Imagine you take a function and you find all the area that's accumulated under its curve. Then you turn around and ask, okay, but what's the rate of change of that area? Well, the answer is just the original function you started with. They're a perfect pair.
Now, part 2. This is the real workhorse. This is the part of the theorem that gives us that incredible shortcut we've been talking about. It tells us that to find the total area under a curve between 2 points, you can forget about all those infinite rectangles. All you have to do is find the antiderivative, which is just the function whose derivative is the one you started with, and then plug in your two endpoints.
And this is absolutely crucial. Part 2 lets us swap an infinitely complicated problem for a really simple two-step algebra calculation. I'm not exaggerating when I say this is the shortcut that completely changed the game of calculus.
Okay, theory is awesome, but let's actually see this shortcut in action. We're going to take this thing for a spin with a real example and see how easy it is. So here's our goal. We want to find the exact area under that simple line, f of x equals 2x, between x equals 1 and x equals 3. You know, before, this would have meant setting up a whole limit problem, but now we use the FTC. Let's just walk through this together. Step 1, we need the antiderivative. So what function gives you 2x when you take its derivative? That's right, x squared. Okay, step 2, we plug our upper number, 3, into that antiderivative. So 3 squared is 9. Step 3, we plug in our lower number, 1. 1 squared is just 1. And now for the final easy step. We just subtract the bottom from the top. 9 minus 1 gives us
8. That's it. No limits, no sigma notation, no infinite sums. The exact area is 8. I mean, come on, it just shows you how unbelievably powerful this theorem really is.
So why is this thing called fundamental? Well, it's because this is the bridge that connects a rate of change to a total amount. Think about a car's velocity. That's just the rate its position is changing. If you integrate that velocity, you get the total distance it traveled. This is exactly how physicists jump between acceleration, velocity, and position. This connection is used absolutely everywhere.
Okay, so this tool is obviously incredibly powerful, but there are a couple of really common traps that you've got to watch out for when you're using it.
First up, the famous plus c. You absolutely need that for what are called indefinite integrals, the general ones. But for definite integrals like the one we just did, the ones with numbers at the top and bottom, the c's would just cancel each other out when you subtract, so you can forget about it. Second, and this is a classic mistake, get the order right. It is always the value at the top number minus the value at the bottom number. F of b minus f of a. Just think top minus bottom. If you get it backwards, your answer is going to have the right number, but the wrong sign.
And there you have it. That's the conceptual key that really unlocks the rest of calculus. See, this isn't just some clever trick. It really is the foundation of the entire subject. You've basically got the conceptual foundation now. You're ready to dive deeper into all the incredible techniques and applications this opens up. Thanks for joining us for this explainer.